So the notes that I'm taking today, oh, you guys need the packets too. They're found on this website. The lady goes through it. It's that Renee McCormick, and that is the link if you want to watch her video. This is being recorded, so you don't have to write it down. But she might offer you additional stuff. She's much smarter than I am, so let me see somebody. Oh, that's right. He's fishing, isn't he? He's fishing too. Huh? The one that says acids and bases here. This is your homework, not the whole thing. I'll tell you how much you're going to do in it. But that's the initial part. Yep. All right, so this is where you can find her video if you want to listen to her talk about this. And then there's several videos in this lecture series. There's part 1, acid base, part 2, and then part 3. And then we go on, page 21 has one on buffers, and that's the one that we're going to spend a considerable amount of time on. A lot of this initial stuff on this video is a review of material that we covered back when we were studying acids and bases. I believe it was unit 4 that we did that in. So a lot of the stuff today is just basic kind of, oh, do you remember we talked about this and that sort of thing. Okay, so acid again means sour. It's Latin for sour. And if you taste stuff that's sour that you don't do in lab, but if you were to do that, it would taste something kind of like a lemon or sour that way. Alkali is Arabic for ashes, and it comes from burning certain plants. Water solutions feel slippery and taste bitter, like soap would be a base. All right. We use them a lot of times all over everything. Like even our bloodstream has to have a certain level of acid base. You can end up with, like in your bloodstream, if you end up with too much carbon dioxide in there, you can end up shifting and making carbonic acid, which then throws off your blood chemistry. And so they look at acids and bases, or the acidity, the pH of your blood when they take your blood. That's one of the factors that they look at. Okay, there's a condition called acidosis, where you can end up having issues with acid in your bloodstream, and it can cause some serious complications. Sulfuric acid is an indicator. So sometimes they're talking about an economic indicator. People will use that sometimes to be able to indicate how industry is doing. Now, there are different definitions of acid base. The Bronsted-Lowry is the one that we use primarily in here, but it's good to know that these other ones exist. Acid donates hydrogen, a base donates hydroxide. The problem with this is that ammonia is a major exception to this. So ammonia is NH3, okay? That's a base. So how can it donate a hydroxide ion when it doesn't have any oxygen in it? Like, it's not possible. And so that's why they kind of got rid of that notion, okay? Bronsted-Lowry then is the one that we use in here. This is going to donate a proton in water, and the base accepts a proton in water. So that helps us with ammonia. So if we had NH3 and we had that in water, okay, wait a minute, doing that right? No, the OH would be over here. So, shoot. There's my eraser. Now I got it to work. But it won't erase that line. I don't know why. More than one way to skin a cat. Okay, so over here, that would be an NH4 plus. And then that would be H2O on this side over here, it would be H3O plus. So here, this would be your acid. This would be your base. You can take the two things, and whatever they are, you can kind of see that these are kind of cousins, right? And then you find the cousin with the most hydrogen, that's your acid. And then the other part of that grouping is going to be your base. Okay. They call the stuff on this side conjugate acid and conjugate base. So this is your base and your conjugate acid for that base. Here's your acid, and this is your conjugate base. If you go on to college, they talk about Lewis acids and bases. Acid is an electron pair acceptor, and the base donates an electron pair. If you get into college, they'll talk about this. We're not spending time here. We don't have it, okay? If you want to listen to her video, though, she does go into this a little bit. And so if you're really interested in it, you're like, oh my gosh, I really want to know about it. Yeah, go out and listen to it. Okay. So Bronsted-Lowry is going to be your concept of acids and bases that we use in here. This is what I was just explaining up above there with this guy. Down here, we talked about the cation as an acid, anion as an acid down here. So when we talk about the conjugate pair bases, one of them is going to have an H plus unit on that, and that would be this one here. Here you've got an H plus here and here. Okay. This would be an H plus here. And then over here you've got this guy, and this guy. Wow. What did I do there? I screwed that up. This guy should not be. I need to get rid of that. Come on. There we go. So this one has more hydrogen over here. So, okay. So in each example of the acid, you're going to note that we're forming H3O plus. This is called a hydronium ion. A lot of times this is written just like this, and it's used interchangeably. So we will use the H3O plus, we will use the H plus, and you'll see them used interchangeably I'm recording, okay, in different things, okay? So this is a hydronium. It's riding piggyback on a water molecule. The water is polar. The charge of that naked proton then is greatly attracted to Mickey's chin. So what they're talking about is that you've got a hydrogen here. You've got a hydrogen here. This is your water molecule. See how that looks like Mickey Mouse? I'm not an artist, y'all. Sorry. And then a hydronium ion would have an extra hydrogen down here. So that's what they're talking about Mickey's chin. Because before I drew that one on, you could see Mickey Mouse there, kind of. Nobody's hiring me to be an artist. I can tell you that right now. All right. So when we have this situation and we're forming NH3 here, okay, we've got NH3, we're adding water. Water's acting as an acid here. Over here, it's going to be giving the hydrogen from that acid to here. This then will be without a hydrogen. So you've got hydroxide ion here. Okay. This is a base. This is its conjugate acid, and we're forming an anion here. Okay. And down here, we're doing the same thing. We're forming these hydroxide ions here. So notice that the hydroxide ions in each of the alkali examples, that species is named the hydroxide ion. It lets you know that the resulting solution is basic. So when you see this, when this is formed, you are going to have a basic solution that's going to occur here. Okay? So in the following reaction, identify the acid on the left and its conjugate base on the right, and identify the base on the left and its conjugate acid on the right. So figure that out here. And then you need to write these reactions when these are placed in water for these other two and see what happens. And then identify those things. All right, so do you see the pair here, the cousins? Find the cousins. And which one has more hydrogen? That's your acid. Conjugate base. Cousins, base, conjugate acid. You do okay there? All right. What would the conjugate base of this look like? If this is the acid, what would the base look like? Well, notice that the base always has one less what? Hydrogen. So what would this look like if I took a hydrogen away from it? With what charge? Minus. Because hydrogen, remember, is a positive charge. So if we're sitting here right now, if hydrogen's a positive 1, we're sitting with a +2 on this side and a -2 over here. If I take a hydrogen away, I've taken a plus away, so now I'm sitting at a +1 and a -2. What's my overall charge? A minus. Does that make sense? Okay. See if you can work with this one. This is where they're wanting the conjugate acid of this one. Figure that one out? Okay, did you get HNO3? No charge, right? Because we added a plus charge in, which took that negative away. All right, so acids only donate one proton at a time. So monoprotic means that it only has one proton, one hydrogen to donate. You can end up with diprotic acids. They would have 2 hydrogens to donate, like H2SO4 or H2CO3. Those would all be diprotic acids. Polyprotic means that we have many hydrogens to donate. Okay? Polyprotic bases then will accept more than one hydrogen ion. They are anions with a -2 or -3 charge. All right, now we can have stuff called amphoteric or amphoteric. Amphi means 2 ways or swapping, so we're able to swap protons. These are molecules that can either act as acids or bases. water is the quintessential example of this. Okay? So if we were to write the dissociation reaction here for hydrochloric, we are not going to put water in that reaction. Okay? So what would that look like? Well, essentially what we're doing is we're breaking down, we're taking our HCl, okay, we're turning it into ions. So if we turn this into ions, and this falls apart, what do we end up with? Correct. And it's balanced. Okay?
Well, what about it being a Brinkelhoff?
Doesn't matter. You don't do Brinkelhoffs with ions. Here's your stuff, honey. That's okay. You said that you might be. Did you catch anything?
Actually, yeah. I caught a lot.
Cool.
One really nice graph, though, otherwise it was a bunch of little blue gills. Definitely fun too.
At least it was a little warmer today. All right. So now we're going to take and do the same thing with acetic acid. So see if you can break acetic acid down. So acetic acid is HC2H3O2. We're going to break that hydrogen ion out. And it's going to have a negative charge on it. Ammonium then is NH4+. So if I break out a hydrogen off of that, it's going to end up being NH3 and no charge because the plus went with this hydrogen. No, no charge. All right, were you able to get those? That's a 2 there. They kind of give you the answers down here, but some of it got cut off a little bit. The subscripts didn't transfer.
For the last one, you take the H off the thing, or just like the H?
I would take it off of here.
Is there any reason why?
Like instead of making it H4,
Oh, like structurally, it would
Yeah.
make no sense. Okay.
So this one would have the nitrogen here, and then you would end up with a hydrogen here, here, and here. And it's more likely to come off of here than it would be to come off of one of these with the hydrogens made.
The H is in the middle, and one like in the front or the end of the writing, you take it off that first.
If it's in the middle,
Well, like, so
I would.
like for D, you have an H in the middle and H at the end. So would you like take the H's off? Like if there's one in the middle, but you have an option of like it in the beginning, you would take the beginning one, or?
I wouldn't, no. I would take the ones on the end down here. But I don't think they'd ever give you anything like that. So that's getting into organic, and I don't think you're ever going to see that. All right. Oh, clock's going crazy. So we need to talk about and remind you about the difference between strength of acid and concentration of acid. Okay. We've had this conversation before. Okay. But now we're going to do it in terms of Ka and Kb. Okay. Because you guys know what K is now. We have Ka and Kb. with these acids and bases. Okay, we had Kp and Kc before. Now we're going to do Ka and Kb. So when we are talking about an acid being strong, what that means is that when we have our HCl here, we have an arrow. That arrow points one direction and only one direction, and all of that material disassociates into ions. That is a strong acid. The Ka value for this is going to be times 10 to the, and it's going to be a positive value here. So it'll be some number here times 10 to the, and there's a positive value. Okay? And what that means is the majority of your material, remember how we figure out a K value, we have the stuff, the products on the top over the reactants on the bottom. That means that our products are going to dominate that situation, right? Okay? That is what makes something a strong acid or a strong base. Hi. Hello. Come on in. You know who you're going after?
Yes, just between
Cadence.
classes.
Oh, between classes?
Yeah,
okay.
fine.
All right.
Thank
you. All right. So we've got weak acids and bases. Weak acids and bases, you will see them indicated. You will end up with like acetic acid. 302. You're going to have a double arrow. It's going to disassociate here into its ions, just like we did in the last exercise. Okay. The Ka value here is going to be something times 10 to the negative something. You're going to have a negative value. What this means is the majority of your material is going to lie over here. You're not going to be producing that many hydrogen ions. And if you remember correctly, it's your hydrogen ions and how many you have of those, that hydrogen concentration, that determines whether something's an acid or a base or not. Because remember, your pH equaled, right, your, what was it for the hydrogen concentration? Your hydrogen concentration, geez, where's my brain at? pH and hydrogen concentration. Yeah. So pH equals, yeah. So your pH, good Lord, my brain is just shot. Yeah, negative log, that's what it is. It's the negative log of this. I don't think I would have ever thought that I would have forgotten that. But if we do, it's on this blue sheet, your cheat sheet, your formula sheet. So I could have gone there. The pH equals the negative log of your H concentration. Okay, and that's what determines if something's an acid or a base. Okay, pOH is the negative log of your OH concentration. Okay, now that's what determines if they are strong or weak. Now, you can still have concentrated acids and bases. Okay, concentration goes down to molarity. So you can have, you know, a molarity of this. It's like a 12 molar acetic acid. Okay, don't get that on yourself. Like, you will hurt yourself. Life will not be good. Okay, even though it's termed weak, it can still do damage. Okay, strong acids, you can dilute these enough that you could actually drink them and be okay. Do I advise doing that? No, don't. But the point is that it can be done.
Too bad Alex wasn't in this.
I know. He'd appreciate it. But you get the idea. Like, you can make this so dilute that it's not going to harm you. Okay? In fact, you know, if you get indigestion, right, sometimes you get the burps and then you like burp up that sour taste and stuff. You're burping up hydrochloric acid. Okay? Now, your stomach lining, inside your stomach, there's a mucus lining in there that protects your stomach from getting eaten away by this hydrochloric acid. Stress and certain foods, caffeinated beverages, different things like that can reduce that mucus lining, and you can end up with something called an ulcer in there where the acid has eaten away. But for the most part, like, you're able to handle a certain amount of this because of that mucus lining. Okay? But you know, that's why people who are like bulimic, they end up with their teeth sometimes rotting out because they're throwing up that acid so much that their body can't flush it out and deal with it properly. People who are meth addicts and they smoke meth, the byproduct of meth, one of the byproducts of smoking that is that they vaporize this hydrochloric acid. They bathe their skin in it, and that's why they look so old so rapidly. That hood, is it pushed down? Yeah, it is.
Yeah.
Cold air comes in through that hood. You can
cold like 90% of the time.
Okay, well, you can move if you want and be warmer. But don't confuse concentration with strength. Okay? It's very easily done. All right. So in AP Chem, for the test, you need to memorize your 6 strong acids. And I told you this back last semester, but hydrochloric, hydrobromic, hydroiodic. These are 3 that you need to memorize. Now notice, what do these 3 have in common?
They're all halogens.
Yes, they're all halogens. HF is missing. Okay, HF is considered a weak acid. Okay, it's considered weak because when that H and that F are together, very few of them, or less than times 10 to the positive, fall apart into this. And that's because the nucleus of this is so tiny and it's close to this hydrogen that those guys end up sticking together more than they pull apart. All right. But like this says, hydrofluoric acid, it's weak because it's small. The electrons aren't shielded. And so because of that, these stick together. But it is very deadly, very deadly. Like, we don't have this stuff here. Okay. No way in the world would I don't even know if we could order it. Not that I would want to. Okay. But it will literally leach calcium from your bones. You have to amputate the bone to be able to deal with it. Yeah, I mean, it's some serious stuff. Okay. So yeah, it's not a good thing at all. So even though it's deemed weak, that doesn't mean that it's not deadly. Okay. So don't mistake its weakness for being okay to be around. You also need to memorize nitric, the first hydrogen of sulfuric. So when you look at sulfuric acid and we're looking to see how it comes apart, we have our H2SO4, and that can't be right, can it?
No, it's not. It's 132.
Okay. I'm like losing it here. Okay, so this hydrogen here, when it comes apart, it's going to look like this. Okay, This hydrogen right here is strong. Okay, so this is going to be this kind of arrow. When we take this, though, the second hydrogen, and we pull it off, it actually is a weak. So the first, they say the first hydrogen from, come on. So the first hydrogen from, piece of junk, come on. There. But then this one is a weak acid. So you'll get a plus here. No, 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 no. Definitely drew this short straw with me, you guys. There we go. Now I'm happy with that. Happier. Still not happy with this arrow here. There we go. Now I'm much happier. All right, so this is a strong. This is a weak. All right, perchloric acid then is the strongest of all, and we'll talk about that on the next page if I have time. This is the strongest of all, and this is going to, yeah, so memorize these 6. These are your 6 that you need to memorize. Don't memorize that one. Some people consider these in college. You may end up with these as well because they're right on the edge. Okay, we get out at 46, right? Okay, so I still have a little time. All right, any questions about any of this stuff? Anything that makes sense? All right, so the more oxygen that you have present in a polyatomic ion of an oxyacid, the stronger the acid is within that group. Okay, now do not use that as an explanation. So if they give you 2 things and they say which one of these is a stronger acid, and you say, oh, the perchloric is, okay, because it's got more oxygen, that doesn't explain it. Okay, that's just showing you a trend. That's not an explanation. And almost all of their questions, almost everything, they ask you which one's stronger. They don't stop there. They always go here. And you know what? They're not going to give you any points for your option A or B. It just tells them whether they need to read on or not. Okay? So you have to explain that. If you don't explain it to them, they're not going to take it. Now, try to explain it in as few words as possible. Make it as succinct as possible. You know, you don't have all day to write a paragraph. But nevertheless, this is what they're looking for, is that explanation. Okay? So within that group, trend. Okay? So first notice the hydrogen of the acid is bound to an oxygen, not to any other non-metal. So here is your hydrogen that you're going to lose. Right here, right here, right here, right here. Okay? Oxygen is very electronegative. So what's going to happen is when that oxygen and that hydrogen are near each other, oxygen is going to take that one little electron that hydrogen has, and it's going to pull it over here. That leaves oxygen with an extra electron, and poor little hydrogen, what's it going to have? Plus charge. That's right. Okay? And it's easy for that little plus charge to float off into nowhere. Okay? You get pulled away. It's gone. Bye. See ya. And that's what your acid is that's the concentration that you're looking for to determine the what the pH is of this solution. So oxygen's very electronegative. It's going to attract the electrons of the OH bond toward itself. If you add more oxygens, you're going to get that more and more and more magnified. So As we add an extra oxygen here, that electron's going to get pulled over even more here. Now we've got 3 oxygens pulling on that guy. It's pulling it over even more. Okay, and that's what they're trying to show you with this arrow getting comically large down here. Okay, so by the time you get 4 oxygens over here, this thing is massive. And it's just pulling that electron away, leaves your hydrogen out here to float la 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 land, and it's gone. Okay, so if you remember right with your acids and your naming and everything, so I'm going to take you back to last year or the year before when we did these. Okay, we had ClO, the -1 charge. Anybody remember what that guy was called? Chloride is just Cl-. Chlorate is down here at ClO3. Chloride is here, ClO2. Perchlorate is down here, ClO4.
Doesn't it look like right there?
Well, let me tell you where perchlorate comes from. It actually comes from hyper, means above, right? Like hypertension, hyperactive. Hypo, yep, this is hypochlorite. Okay, so what we do in science, in chemistry though, is we just say biology B whatever, and we just take the HY off. So that's where that's where the per comes from. So when you guys learn to write those formulas and everything, that's where we got the per. It's actually from hyper. Okay. So with the hydrogen, when we form an acid here, this would be perchloric acid, chloric acid, chlorous acid, and hypochlorous acid. All right. So we also have strong bases. And what you do for the strong bases is you will look at, to memorize those, you just look at your periodic table. Okay. So it starts at lithium. So lithium, sodium, and potassium. Then we kick over, we go calcium, strontium, barium. And then all you have to do is add a hydroxide to that. So lithium hydroxide, sodium hydroxide, potassium hydroxide. When you get to the calcium, though, you have to add a CaOH2. So SR, don't put a 2 there, that doesn't need a 2. SrOH2, and then BaOH2. Okay, so those are your 6 strong bases that you have to memorize. All right. Oh, they fixed the clock now. Okay, good. All right, so when we talk about acid strength or base strength, if our Ka value is very large, then it's going to be a strong acid. If it's weak, then the Ka value will be small. Position of disassociation is going to be far to the right here. So this would be like for your acids. HCl would be strong. Solid arrow, just one direction. Your hydrogen goes here. Your chlorine is here. It's far to the right. When we talk about a weak acid, well, let's just use HF because it's smaller to use. We always have an arrow pointing both directions. We have our hydrogen. We have our fluorine coming off, but most of it lies here. The equilibrium concentration of your H compared to the original value is approximately equal here. And then over here, it's going to fall far to where your acid is mostly here. Okay. Your Ka is your acid dissociation constant. If you have a strong base, a weak acid is its conjugate, and vice versa. Most of your acids and bases are weak, which means that they are not going to ionize very easily. This should be an arrow here. Sorry. For your, when you do your Ka values, you do not include water in the Ka value. So you ignore the water. It should not be reported in a Ka value. Remember that this is the same as H+. So if you see H3O+, it's the same thing as H+. Because it's just in water, we don't include the water. Okay? For weak acids, again, that value is going to be much less than 1. So that's why I said it's going to be something times 10 to the negative value. And you can see here that we have all of these would be considered weak acids. So write the dissociation equation for acetic acid. Acetic acid is HC2H3O2. So write the dissociation reaction for that, and then write the Ka equilibrium expression. I don't want you calculating it. I just want you to show me the expression for it. We get out now?
Yeah,
We do. Okay. I don't know why they're not working. All right. We'll pick up there tomorrow then.
Are we just doing?
I'll give you homework tonight. I'm going to post it sometime next hour. So just look for the post and it'll tell you how far to go in the packet. Okay?
So before I was diagnosed, I went into diabetic ketoacidosis. And now that makes sense because people say your blood is like acid when that happens.
Yeah.
And it shuts down all your organs.
Yeah.
So I was like, I wonder why.
Yeah.